Hi, Dr. John here for extraktLAB. How are you guys doing? Hey, today we're going to be talking a little bit about remediation for THC from CBD. There's a lot of different ideas about how to do it, and we're going to be comparing and contrasting separations versus degradation or decomposition reactions for the remediation of THC. So stay tuned. There are many thousands of compounds in cannabis oil. On this slide, we list a whole bunch of different types of categories, along with some of the known identified compounds and the numbers of the known identified compounds that you find in cannabis oil. If you've ever looked at a GCMS chromatogram, you can see that there's thousands of compounds in there, and those are the only ones that are GC amenable in terms of the ability to measure them. So you have everything from cannabinoids to fatty acids to ketones, different types of aldehydes, vitamins. There are things like esters, steroids. There's also amine compounds. So these are the things that you need to be thinking about when you remediate the compounds that you are looking to remediate, which is the cannabis oil. And that is what happens to all these other compounds. Are they reacting with each other? Are they reacting with the cannabinoids? Are they degrading? Are any of those compounds that are in the cannabis oil, beneficial? And are you taking away all those beneficial benefits by doing the remediation? So these are some of the things that we're going to explore in this presentation. So the first thing we're going to really look at is degradation reactions. What is a degradation reaction? Well, you take some oil, and oftentimes it has much more CBD in it and a very small amount of THC, and you put that into a reactor. You may add some solvent to it, but essentially what you're doing is you're putting it into a reactor and heating it up to 150 degrees Celsius plus. When you do that, you're adding heat energy in there, and all the components of the oil start to react. They either start to degrade, or they'll react with each other, or they'll react with other components, and in that way you can degrade THC out of the oil just by heating it up and degrading it. There are a couple different things that you need to think about when you are doing degradation reactions. The first thing is it breaks down the beneficial and medicinal compounds that are in there in addition to the THC. So if you have beneficial terpenes in there of any kind, if you have if you have flavonoids in there, which are known to be health benefit, then you are basically getting rid of those, or very likely you are losing those trace components that really have a good impact on the entourage effect. The other thing that you're producing is a lot of side reactions between the compounds that are in there. There are many thousands of compounds, of course, and when you have all these side reactions, you don't really know what the products are. So some of them may be beneficial, some of them may be not so beneficial. You just don't know. If you compare a chromatogram of a reacted degraded sample to an original sample, originally extracted sample, you can see that there's major differences in the peaks and in the relative intensities or the relative amounts of each of the different compounds within the system. So they're different compounds and they're in there at different amounts, and we don't really know what they are. You'd have to really go in, and it would be a huge project to find out exactly what each of those degradation components are. That means that it's really not very selective of technique. And what I mean by selectivity is if I was to degrade THC selectively, THC would be degraded and not anything else. Okay, so what's actually happening is the CBD is being degraded, the THC is being degraded, and all the other components are also being degraded and reacting with each other. So it's highly non-selective. So here's some data that we took heating up some oils and degrading those oils. It had a certain amount of THC and it had a certain amount of CBD, and what we were creating was CBN and a lot of other byproducts. And basically what we did was we heated the oil. We started with a reactor, and this one was 158, this was 170 degrees, and this is 240 degrees. And you can see that the CBD went down considerably. You can arrest that if you are willing to take more of the THC, but you can see at 158, we definitely get a degradation of THC. We definitely get a degradation of CBD, and you can see we're also creating CBN. And you can see that this was over 48 hours. If you increase the temperature to 170 degrees Celsius under a stirred reactor, similar conditions, going 24 hours, you can see again you're going from 40 to 19. That's you're reducing the amount by half. You're also going from 22 to 6.9, and you're also creating more CBN. So this looks like it has some promise. If you can keep going, maybe this will go to 0 and this will go to 10, and you'll have a 10% CBD solution with a bunch of CBN in it. So that would be the 170C. Here you have 240 degrees Celsius, and you can see we're going all the way down to 0% CBD. We still have a little bit of THC left, and you can see this is right around 10 hours. So that's at 240 degrees Celsius. So you'd think you do a very high temperature stirred reactor, open to the atmosphere. You certainly can get rid of all the THC, but you're also losing all the CBD. Now, you can see that there's not a lot of mass balance here. Like the CBD is not going over to CBN stoichiometrically, or the THC going over to CBN stoichiometrically either. You're starting off with a 37-21% solution, so it's a pretty high concentration THC, pretty high concentration CBD. And so where's all that CBD and THC going? Well, it's being reacted with other things. It's turning into different types of compounds. So it's one of those things that you really need to think about when you are doing degradation reactions. What is it that you're degrading to? And what is the identity of what you're degrading to? And is it creating unknown molecules with unknown effects on people? So that's something you need to be thinking about. So advanced oxidation processes are well known in industry. Oftentimes they're combinations of heavily oxidating compounds or light, for example, UV light, high energy compounds, and heat in some sort of an exchange process. So in this case, we've looked at ozone. We've also looked at UV light. And sure enough, it definitely will do the job. I mean, it will take out the THC, but you'll also see that there are side reactions that occur. It's not stoichiometric, meaning there are other things that are happening. In this example right here, we have ozone at 175 degrees. We're bubbling it up through. We have a stirred reactor holding it at 175. You can see after 22 hours, the CBD degrades from 41 to 24%. The THC definitely goes down from 22% to 6%, and the CBN here basically increases to 7%. So that's something you need to be thinking about when you're dealing with degradation reactions. You can see that it takes a long time here for THC to degrade all the way to 0. This is at 210. You can see we're losing the vast majority of the CBD. And at 21 hours, you can see that it's becoming quite a bit of CBN is left in the reactor. So what if you only had like 5% THC and you were degrading it? We found out that the timing is about the same. If you're starting off with, say, 6, you're still degrading quite a bit of the CBD down, half, and it doesn't really matter. It still takes a long time, and you still have the same amount of degradation of your CBD, and you also are creating CBN. So one of the benefits to the degradation pathway for remediation of THC from CBD solutions is the simplicity of the apparatus. So you just need a stirred reactor of some kind with a temperature controller. If you're going to add solvent in, you need some sort of reflux so that you're not losing all your solvent. So that's a stirred reactor with reflux condenser. Open to the atmosphere or ozone bubble. Sometimes you can use one of these holes here with a stopper and a hose going down here so you can bubble it up through to create basically an ozone environment above it as it's being stirred. It's simple, it's well known. A lot of people can use it, and you can use multiple reactors if you want to go really slow and a long time, you can do that. So that's the type of thing that you would use with a degradation apparatus. So what are the pros and cons of degradation? We've kind of touched on them all, but here's a summary sheet for you. The pros are that the apparatus itself is very inexpensive and it's scalable. So if you are happy with 20 liters, you can probably scale to 50 liters. If you're happy with 50 liters, you can scale to multiple 50 liters. and you can do a lot of the oil all at the same time. And that is quite inexpensive to do. You don't need to have very advanced people to do that as well. So, the labor is relatively inexpensive as well. So the cons, of course, is that you are creating a lot of unknowns. You're creating side reactions. You're creating a whole litany of reactions. You're degrading possibly even all of the beneficial aspects of the oil just to get out, 5% or 10% of THC. Non-selective, no concept of separation. It's not selective. In other words, temperature acts on all different molecules pretty much the same way. You just need to provide enough energy to go over the activation barriers for the reaction. So, and everything, the thousands of compounds that are in there are all reacting with each other. So it's really not selective. And there's really no concept of separation efficiency. For example, if I'm trying to separate out THC from CBD, the question would be, why is it that, how do you separate those out and still maintain the amount that you had in the very beginning of the solution? So there really is no concept of the separation efficiency. It's just degradation only. And because of that, you get this low yield and high loss. So now we're going to talk about chromatography as an alternative to degradation. And really what chromatography is it's a separation technique. Separations really maintain the integrity of the sample. And there are basically 4 key benefits to doing separations versus degradation. The first is that it's very selective. You can basically do the separation. It'll separate out the components from each other rather than degrading the whole mixture. It also is very high yield. Oftentimes you have losses associated with a particular method. In the case of degradation, we saw that CBD was degrading to something else. We didn't know what it was, or maybe it was degrading to CBN, but maybe it was degrading to other things and reacting with other things. So in the case of chromatography, however, really the only losses that you're going to experience are those that come from transfer losses. In other words, if you're moving oil from one vessel to another, typically there's a transfer loss anywhere from 2 to 5%. It's not really coming from the process itself. Number 2 or number 3, the high integrity. It won't actually create new compounds or side reactions. So you won't see an injection of your oil onto the column and then have different compounds come out unless it's catalytic or unless it's at very high temperature. And chromatography typically is not run under high temperature catalytic conditions. So it's very high integrity in terms of the process. The fourth thing is that it's a ubiquitous technique. It's used throughout chemical, pharma, food, and nutraceutical industries. There's a huge body of knowledge and also practitioners who do chromatography techniques. So if you have an issue, you can technically go and try to find someone to help you with the issue, or if you want to do a different type of separation, there's a tremendous body of literature out there that you can access and really use the versatility of your machine rather than just trying to cook it up. So this is the separations apparatus. You can see here's the column right here. The column is where you add media. This is the pump that pumps solvent. And back here, there's an injector. The injector will take the sample and inject it onto the column while the solvent is running, and then we call that the eluent. And so what happens is the compounds that are on the column will separate based on their affinity for the mobile phase or for the eluent or the solid phase that's packed in here, which is what we call the media. And that's how you get separations. And how good it is depends primarily on what we call the selectivity. And so the more selective the separation, the greater the peak separation between the main components. So the rest of this apparatus is really conditioning for the pumps, and then on the backside here, solvent recovery. And this is one of the main reasons why people like our system is that we really are we are the only company in the world that has online solvent recovery built into the skid. So here's an illustration of the high yield, high recovery aspects of chromatography. Basically, here's your sample and you're injecting it on with an injection pump. We do high pressure injection. Here's your main pump, it's pumping in, and then the column is separating. So you can see you're getting out one peak here. If you inject double, you get 99% recovery. So we really measure the peak area and then under this peak here, and we can say, okay, well, we get a 99% recovery. If you put 1 gram on, you get 1 gram off. You inject the double and the peak area should double. So those are some very easy ways that you can use the equipment to actually tell if your recovery is up to par. So on-column losses are very small, less than 1% in the case of CBD and THC. If the loss is large, then that method could be developed and used selectively. It really, the on-column losses really are highly impacted by the method that you're using. In our experience, we don't get any loss and we can really clean the column quite well. Losses to the apparatus are very small once the apparatus is flushed properly. So you will have, analytes sticking to the walls and getting caught in the crevices and whatnot within the equipment. The equipment has been designed for cleanability, so you should be able to clean it out. And then you can actually use that cleaning solution and you can recover the rest of the cannabinoids from that cleaning solution. So that you can even recover at that point. And then losses come primarily from transfer between vessels. We had talked about that, not the process, and the transfer losses on average are 2 to 5%. One of the main benefits of chromatography is its ability to selectively separate out components. That's illustrated by this graph here. Here you have the blue compound and here you have the red compound. You can see that in time, this is time and this is concentration. You can see that they're separated out in time. So I can take this peak, which represents essentially the first compound, and put it into one vessel, and this peak, which represents the second compound, and put it into another vessel. This is essentially what preparative chromatography is all about. This is an idealized case. Oftentimes you are running these samples and in very high concentrations on the column. So there's certain things that you need to do and a certain skill set that you need to maintain this selectivity. But basically you can also change and optimize the selectivity for different compounds. And that's why chromatography is such a great technique, because you can change the stationary phase and that will have a different selectivity for these different compounds. It could be that if you change the stationary phase, there would be no separation at all. Or you could change the separation, the stationary phase, and the red one might come out first instead of the blue one. So this is things that you can do to move these peaks around relative to one another. And that's really what methods development is about. That's why you have chromatographers who do that type of thing. There are also things that you can do to change the selectivity with like polar solvents, non-polar solvents. You can use like chiral stationary phases, for example, and those things really get amazing selectivity. The more selectivity that is built into a material, probably the more expensive that material is going to be, just as a general rule of thumb. So if you buy a chiral chromatography phase, it's going to be very, very inexpensive. If, on the other hand, you buy a kind of a non-selective phase, like, for example, silica, and you still have enough selectivity to make a separation, then you buy the inexpensive phase. And that's what a lot of people do in remediation of THC from CBD. They buy the inexpensive phase and they have a method, which is probably a normal phase method, to do that separation. So separations are also very gentle. They are not using high temperatures in the column to do the separation. So what happens is, as you add the oil to the column, it's non-reactive and it won't create new compounds and it won't create unknowns. So typical temperatures are 35 to 40 degrees. It's not enough to facilitate reactions. Typical solvents are nonpolar or polar modifiers. They're non-reactive. In fact, the solvent must be selected to be non-reactive. There's no reason to have a reactive solvent. They'll include like pentane, methanol, ethanol, water, heptane, for example, might be another good typical solvent. And then also typical pressure for a column, 3 to 500 psi. Even if this number was up at the 4,000, 5,000 psi, it would have no or little to no effect on the reactivity of the components in the analyte. So what are some of the main reasons people do not use chromatography? Well, there are three main reasons if I were to put my finger on them. The first one would be the idea that the media or the stationary phase costs a lot of money. Some companies have gone to market with what they call cartridges, and the cartridges are pre-packed columns, and you put those into the system, and when they foul out, for example, you will replace the cartridge. So cartridge cost is a big factor in the cost of running a chromatography system. Some manufacturers allow a customer to pack their own media into their own columns and then sell them bulk media. So that's in our case, we have the ability of the customer to pack their own columns, and the bulk media is pretty inexpensive. You're looking at basically 500 to 10,000 per kilo. The non-selective phases or the less selective phases such as C18 or silica or single mono phases, they're very inexpensive, and there's many different vendors that you can buy those from in bulk. So the price is really low. The higher end phases that I was talking about, like $10,000 per kilo, those are the selective phases. So oftentimes they'll be like chiral stationary phases, or they'll be size exclusion phases, or things along those lines. If you're talking about just THC and CBD, you are talking about very low cost stationary phases on the order of, basically 500 to 1,000 or 500 to $2,000 a kilo. So depending on who you're dealing with. Also, the high solvent cost, solvent and solvent loss and solvent handling leads to high cost, and then the cost of the solvent itself is very expensive. So this is a key issue associated with chromatography, is that high solvent cost. It's a really big problem. You're talking about lots of losses. You're talking about handling. You're talking about moving solvents. Even if it's somewhat automated, you have a lot of management intensity that goes on with that. Maybe you have to have a facility that's been rated for that. So management of personnel, solvent media, quality can be a large management task depending on the type of equipment, number of pieces of equipment, and automation. A lot of people in the cannabis industry will buy small systems, and they'll try to run like 6 or 7 of them at a time to create a couple kilos a day worth of oil that has been remediated. The problem with that obviously is that it's just a management nightmare. And so one of the things that you need to do if you find yourself in that situation is to look at our Pure 99 system, which really solves these three issues. One of them is the high media cost, the high solvent cost, and the management intensity. And I'm going to talk about that next. So the Pure 99 solves the drawbacks that we just talked about and offers the lowest cost operation. So in terms of media, you can pack your own. Like I said, the costs are 500 to 10,000 per kilo. You would be using this lower range if you are doing CBD THC remediation. 1,500 to 2,000 per kilo. Lifetime is 6 to 9 months. You can clean it out. Oftentimes you can remediate that if you want to. So you really shouldn't be changing out your columns that much. If you have good sample prep, in other words, if you are putting very nasty unprepared samples onto the column, the lifetime is going to go down. So that's something you need to think about. So sample prep is a big deal. And then cost increases as selectivity increases. That's that 10,000 per kilo. That's, for example, selective phases such as chiral phases that are proprietary. They're expensive. And there are many suppliers. So in terms of media, you can do material sourcing, look around for the best price and go ahead and get that. Automated online solvent recovery is our claim to fame. We have little to no solvent is used per day with the online solvent recovery. It's really sweet. It basically has 3 falling films attached to it, and you really create a method that is not only a separations method, but also a distillation method, so that you can distill and recycle the solvents right online as you're going along. So, and then you can recondition the solvents with the various sensors and verify that the solvents have been reconditioned with the various sensors that are on the unit. And so really there is a 2-step method development process with the Pure 99 versus a 1-step with just a regular system. And you're really getting the benefit of all of that automated solvent online recovery. Also, your management intensity goes way down. So your chaos goes down, the amount of inventory you have that's going down, the number of quality checkpoints that you have also goes down. So a lot of benefits to implementing the Pure 99 into your workflow. So in conclusion, here's a comparison of degradation and separation for remediation of THC and CBD. I always like to put a summary table together so that you guys have all of the information that we talked about. First of all, selectivity. Degradation really doesn't have a selective degradation with heat or ozone. It's basically as you add the heat in, or as you add the heavy oxidant in, it's going to react with everything. On the other hand, separation is tunable. It's selective separation, and it doesn't degrade any of the components that are in the oil. The yield typically with the degradation is low. Separation is very high. Side reactions, there are no side reactions with the separation, but on the degradation side, there's a lot of side reactions that are occurring. You get a high degree, many new compounds. You can degrade what we call the beneficial or maybe the medicinal compounds, the low-level compounds that are in there, which is called the entourage effect, for example, or maybe you would be sacrificing your full spectrum. The other minor cannabinoids that are in that oil may also be degrading to nothing. The natural aromas, of course, will be gone, and the flavors will be gone too. So those are things that you need to be thinking about when you do degradation. The conditions obviously are high temp and oxidizing. You don't necessarily have to have a super oxidizing or advanced oxidation process environment with like UV or ozone to get it done. You can just wait a long time. It's gentle as opposed to separations, which are gentle, typically done at room temperature. Cost is very low. That's the main thing, main benefit to degradation. Whereas the separation, you can range from anywhere from 150 to 500,000. So you really need to look at the cost benefit of what you're really doing. One of the things that is also important, what is a key benefit to degradation, is that the simplicity of it is quite easy. You have the degradation, you have the reactor, you have stirred reactors, multiple stirred reactors, you turn them on and just let them sit there, and then maybe test them out over time. So if you don't mind all the side reactions and unknowns and degradation and loss of the entourage effect and all that, then maybe it's the one for you. On the other hand, you're going to need to have some sort of skilled operator associated with the separation side. Also versatility, there really isn't any versatility. So once you get this, set up here and you're doing it for degradation, I guess you can repurpose the reactors to other things if you're not doing it anymore. But in the case of the separations, you have the ability, you're basically building capability versus just stirring something up and reacting it. So this is the capability that many pharmaceutical companies have, and what many aspiring pharmaceutical and nutraceutical companies need, and that is, are we able to isolate the different components, and are we able to scale that up, and then are we able to do a clinical trial on that just to show that, hey, there's a beneficial effect on, for example, this combination or ratio of flavonoids or amines or polyphenols. This is really the essence of biological medicines. And then adoption of technology for separations. The other thing is that, obviously you have a whole list of people and professors and papers. If you need to separate out something, you can go to the literature. It's very nice to have that. With degradation compounds, you're probably looking at, you're looking at the literature too, but you're looking at the organic chemistry literature. It's going to be isolated to 1 or 2 compounds, and you're really not going to be talking about a biological oil that has many, many hundreds of compounds in it. So it's a very limited technique. So thank you so much for joining us. I appreciate it, and I hope this helped in terms of your abilities to understand the differences between degradation and separation for a THC remediation.